Okay, so if we were to now determine delta H. So remember, we're going to add up all of the product delta HFs, including taking into consideration the moles. So let's take a look. So we would have 1 mole of CO2 times the value for CO2 delta HF, kilojoules per mole, right? Plus, we have 2 moles worth of water, and we would multiply that by the value for the delta HF of water. Okay, so what we've just done there is this first part, the delta HF of the products, and it's the sum of them times their molar value. So remember, the mole value we get from the coefficient. So we have 1 carbon dioxide plus 2 waters. We're then going to subtract the reactants in the same way. So we have 1 mole of methane times the value of methane, which is negative 74.4 kilojoules per mole. And then actually we have 2 moles of oxygen, but that is going to be 0 anyways, right? So it's 2 times 0, which is 0. So what we just did there was our reactant values. So we had 1 mole of methane plus 2 moles worth of oxygen, which happens to be 0. Okay, so if you were to work this out, 1 times negative 393.5 plus 2 times negative 241.8 minus 1 times negative 74.4, we get a value of negative 802.7 kilojoules. Okay, which if you recall is the same value we got when we did Hess's law. Now, again, we still want the molar enthalpy for the combustion of methane. However, this is also representing 1 mole. So essentially, this is going to be already the molar enthalpy. So we have 1 mole of methane, so it ends up being negative 802.7 kilojoules per mole. Okay, so it's exactly the same value that we received when we did our Hess's law version of this. So this is just an alternate way of determining the delta H for a reaction, which can then be the molar enthalpy for that reaction. So typically the question will be specific into which method you're using. Of course, if it's Hess's law, you have to be given the mechanism. When you're not using Hess's law, you don't have to be given a mechanism. You can just be told what the reaction is and you're using your reference numbers to calculate it. So usually it'll say using, molar enthalpies of formation, determine blah, 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 blah. If it's Hess's law, you have to be given the mechanism. There's no other way for that. Okay, so I have one here for you to give it a try. Can't really get that all in one page, can I? Okay, anyways, I'll shift it. So I'd like you to pause the video after we finish going through this, because at this point in time, you should be able to complete this question. So it says, 1 way to heat water in a home is to burn propane. If 3.20 grams of propane burns, okay, which essentially means it's going to be combusted, what temperature change will be observed if all the heat from combustion transfers into 4 kilograms of water? Now, it doesn't say this in this question, but I would like you to using delta HF values. So I want you to answer this question using the delta H of formation that we just learned about in order to get your enthalpy change. Okay, give this a try. This should probably, at this point, your first time doing something like this, it'll probably take you about 10 minutes to complete. If at any point in time you're not able to do this, obviously just continue watching the video. But like I said, after we're essentially finished chapter 5 at this point, You should be able to do this. So give that a try. Okay, so let's take a look at how we would go about solving for this. Okay, so first of all, if you don't have an overall reaction given to you, I would suggest you do that first. Okay, that should kind of be a given at this point in time. You have to have a kind of a goal that you are looking towards. So here we have the complete combustion of propane. Okay, so we're going to use delta. Let's determine the enthalpy change using delta H of formation. So it's all of your products minus all of your reactants. So it's 3 moles of carbon dioxide plus 4 moles of gaseous water. So these are all of our products added minus the reactants. So 1 mole of propane, and then of course plus 5 moles worth of oxygen, which are 0. So I'm not including that here. So this delta H value, negative 2043 kilojoules, also happens to be the molar enthalpy for combustion because, of course, we have 1 mole of propane that is in this reaction. So here we have our molar enthalpy. So then we have to determine, remember the goal of this is to do temperature change. So the only thing we've seen that has temperature change is where we incorporate our heat value into this. Okay, so because we have the molar enthalpy, we have to first figure out, well, how many moles are actually burning. So our system is 3.20 grams of propane. So we have mole over the molar mass to determine our mole value, right? So we don't have 1 mole burning. We have 0.0725 moles. So that will give us our overall energy change for that amount of propane. This 4 kilograms of water, so our propane is the system. The water where that heat is transferring into is the surroundings. Right? So this goes back to the beginning part of this unit. So the mass of water is 4,000 grams, or the 4 kilograms. The heat capacity of water, of course, is 4.18 joules per gram per degree Celsius. So we're using our kind of combo equation that involves our Q, our delta H, and our molar enthalpy. So this is our, if you go back to your molar enthalpies lesson, right? This is where we first learned about this. So the delta HR for the molar enthalpy, we solved for this. That's what we have over here. Now, the only thing is that because our mass is going to be grams and our heat capacity is joules per gram per degree Celsius, since this is joules, that means that our delta HR here has to be joules. Okay, the units must be consistent. Joules per gram per degree Celsius, that means that your energy value must be joules and your mass value must be grams, or else you won't have any unit cancellation happening. So we have, and I made a note down here, so we have here our delta H, the molar enthalpy for the combustion of propane, and then we have equals minus mass of water, heat capacity of water, change in temperature of water. Remember, everything in this bracket is for the surroundings, water, water, water. The mole value is the mole value of the system, which goes back to our propane for this particular scenario. So our change in temperature should be 8.9 degrees Celsius. And of course, that is a positive, which makes sense because this is an exothermic reaction, right? We have a negative delta H. That means our Q should be positive. Our delta T should be positive. So this question is kind of nice. It incorporates a lot of what we've done in chapter 5. The only thing it doesn't include really is Hess's law, but it does include a bunch of different concepts in one spot. And that essentially is the end of our chapter 5.